Before we can solve equations, we need to have a solid understanding of what equations are. An equation is a statement that two algebraic expressions are equal to one another. An algebraic expression can be anything from a single value to a series of terms. These are the same algebraic expressions that you've substituted values into or simplified in the past. What put those algebraic expressions apart from an equation is that an equation has an equal sign. We can think of an equation as a scale. Each side is balanced. If you do anything to one side, you have to do it to the other side of the balance. If I add a mass to the right side, I have to add it to the left side, or it'll be unbalanced. If I take a mass off the left side, I have to take it off the right side, or the scale will be unbalanced. Look at this example scale. There are 2 triangles on the left side and 6 circles on the right side. They have to be equal to each other. The scale is balanced, so the equation is balanced. If I were to solve this equation to find out what a triangle equals, I would end up finding that there's 1 triangle for every 3 circles. In this case, we can just count it out. In order to solve equations, we need to use inverse operations. Try this on your own. Pick a number. So for example, I'll use 3. Add 5 to that number. 3 plus 5 gives you 8. I'm going to take that same value, 8, that I just got, that new sum, and subtract 5 from it. So I took 3, I added 5, I took that sum and subtracted 5. I end up back at 3. I used the same value, 5, but opposite or inverse operations. In your own words, what is the relationship between addition and subtraction? Use this example to describe how they're related and how they affect each other, if they're used in the same problem like this. An inverse operation is an operation that undoes the effects of another operation or function. In the example above, when I added 5, I had 8. When I took away 5 or subtracted 5, I went right back to 3. The subtraction undid or reversed the addition. When I use the same value in inverse operations, I get what's called an identity. 3 plus 5 minus 5 gives us 3. Plus 5 minus 5 has an identity of 0. It's almost like we're adding 0 to 3. We observe it as these operations undoing each other. So we ended up at the value that we started at. Since addition and subtraction do the exact opposite of one another, they are inverse operations. Addition and subtraction cancel each other out, leaving a variable by itself in an equation. That's the goal of solving an equation. We need to get the variable in question by itself. Just like we got the triangle by itself and had it equal to a number of circles, we're looking at a variable all by itself. We pull apart those other values or move them from one side of the equation to the other using our inverse operations. There are different ways to think about what solving an equation is. At its most challenging and more correct level, we can think of solving an equation as mathematically determining the known value represented by a variable or variables that makes the statement true. An example of a true statement would be 1 plus 2 equals 3. If we can find a value for an unknown variable that makes the equation a true statement, we know we've solved the equation. On a more easy to understand level, we can describe what solving an equation is based on how we solve the equation. In order to solve equations, we're using inverse operations to move values from one side of an equation to the other, keeping the equation balanced. By using our inverse operations, we're really creating identities. When we subtract 5 from positive 5, we're equaling 0. Since we have to keep things balanced, we're also subtracting 5 from the other side. So we sometimes observe the value moving from one side to the other, when in reality it's being canceled on one side by finding the identity of addition-subtraction, or it's being added or subtracted to the opposite side, changing the values on the opposite side of the equation. At its simplest, an equation is getting a variable by itself. We use our inverse operations to get the variable by itself. That variable represents the known value of an unknown variable that makes the statement true. So level 3 is the simplest way to describe, but it covers all of our bases. Let's try solving a one-step equation. Here we have 12 equals x plus 6. On your own, what does x equal? Try this problem using any means possible. Now let's look at the step-by-step process for solving a one-step equation using addition or subtraction. This is the same general steps that we'll follow whenever solving any type of equation. This lesson just happens to focus on addition-subtraction in one-step equations. When I start my equation, I ask myself, what is happening to the variable? This is a step that if you'd like to write out, it may help, but it can also just be a conversation you have with yourself. I look at the equation x minus 5 equals 12. What is happening to my variable? X minus 5. So I'm taking the value x and I'm subtracting 5 from it. I'm subtracting 5 from my variable, so that helps me answer my next question. How do I undo the operation? This is a simple way of asking what is the inverse operation. If I'm subtracting 5, I need to add 5. These two questions are the most important yet most often overlooked steps in solving any equation. This helps us decide which values to use. We're not just solving or evaluating an algebraic expression, where all of the values, all of the expressions, all of the operations are right in front of us. We need to use inverse operation. So now I'm going to apply the appropriate inverse operation to both sides of the equation in order to keep the equation balanced. I said that I'm subtracting 5, so I need to add 5. Addition, subtraction are inverse operations. If I add on the left, I need to add on the right in order to keep things balanced. Now I'm going to evaluate each side of the equation. Look at things as terms. Negative 5 plus positive 5 gives me 0. That's a quick calculator moment. I also should recognize that when I add positive 5, or when I add 5 and subtract 5, I end up with my identity of 0. This is why we say sometimes that it cancels out, leaving us with just x on the left side. X plus 0 equals x. 12 plus 5 is going to give me 17. Because that 0 is a little redundant, we don't need it, my actual solution is x equals 17. Your final solution should represent those 3 levels of understanding what an equation is. I have my variable by itself. X is off on one side, all the values are off on the right side. I used my inverse operation to move that negative 5 from one side to the other, so the variable is all by itself. I did that by finding my identity. Negative 5 or minus 5 plus 5 gives me 0. So it canceled on one side and it changed the value on the right side, keeping the equation balanced. And at the highest level of understanding what an equation is, x equals 17 represents a value that could be substituted in to create a true statement. 17 minus 5 does in fact equal 12. Let's apply this process to a couple of equations together. 23 equals negative 12 plus y. First step, ask yourself, what's happening to my variable? Equations written like this, where the variable does not come before any of the values or operations, can oftentimes be confusing. The question is, what's happening to my variable, not what is my variable doing? A lot of students look at this problem and say, I'm adding 12. Well, I'm adding y, but I'm subtracting 12 from y. I could rewrite that problem as y minus 12. If you see an equation where there's a value, especially if it has a negative sign in front of it like this, and then it's being added to the variable by itself, assume that the sign is equal to the operation. If it's a positive 12, that'd be plus 12. If it's a negative 12, it's minus 12. Negatives act the same as subtraction. We're taking away values. So my second question, if I know what's happening to my variable, I have to ask myself, how do I undo it? The inverse operation for subtraction is addition, so I'm going to add 12 to both sides of the equation. When I add it to the left side, 23 plus 12 gives me 35. That can be a little calculator moment. We're breaking it down into easy little steps instead of looking at the whole equation as one big challenge problem. Negative 12 plus positive 12. That gives us our identity of 0. 0 plus y. Anything plus 0 is just itself, so my solution is y equals 35. 35 equals y is a perfectly acceptable way to write it as well. My variable is all by itself on one side with the other values on the left side. I got those values moved over by canceling out or finding the identity using my inverse operations. And I now know that if I plugged in 35 for y, 35 plus negative 12 would give me 23. An equation with decimals does not at all change how we attempt the problem. Equations are all about the operation, not about the form of the values in the equation. X plus 5.2 equals 7.1. I need to ask myself two questions. What's happening to my variable? How do I undo that operation? So I have x plus 5.2. What's happening to my variable? I'm adding 5.2 to x. So I'm adding 5.2. Inverse of addition is subtraction. So I know it's adding 5.2. To undo that, I need to subtract 5.2. So I'm going to subtract or minus 5.2. I do it to both sides. Take the time to write out the operation and the value that you are applying to either side of the equation. 5.2 minus 5.2 gives me 0. That's my identity for addition subtraction. So I end up with x plus 0, not y. A little typo there. 7.1 plus negative 5.2, or 7.1 minus 5.2. Little calculator moment will give you 1.9. So x equals 1.9. I have my variable all by itself. I got it all by itself by using my inverse operations. Those inverse operations helped me cancel out using the identity 5.2, which left the x all by itself. I now know that if I plugged in 1.9 for x in my original equation, 1.9 plus 5.2 would equal 7.1. It would give me a true statement. On your own, try the last two problems. Ask yourself the two questions: what's happening to the variable? How do I undo that? And then apply those inverse operations to both sides to keep the equation balanced, and just simply evaluate.